when there are no effects at all. When you add the bonds, it's quite interesting that there's not. It's a very small effect for these covalent explosion rates. When you add the secondary ionization, it's a big deal. And then you add the bond breaking, it's a little bit. And the molecular phase, of course, I already showed you how it changed, the charge state distribution. But the big thing is that, well, of course, all effects are required to get an agreement on the order of 20%, but secondary ionization is really the most important thing. So if I just summarize, what I sort of went through, is that the theoretical modeling really reproduces the C60 response. And the way they treat it is not so difficult. I mean, we can even do this at Argonne. It's not that difficult, right? First, you treat the C60 as 60 individual carbon atoms for photoionization. You can track all these electronic configurations. You can calculate the cross sections by, that X atom code that I told you about. The C60 was held together with some particular force field for all the bonds, which we already saw was not so important. And then the new electrons are created when they're created with their appropriate kinetic energies, and you just propagate everything classically and see what happens. And then, you might have to add you add these other effects that have to do with the fact that it's a C60 versus molecule. But all these things are practical. Secondary ionization is the most important molecular effect, and the other thing that's quite interesting, the high fluids ultra-short pulse regime, you actually neglect the chemical bonding. So it's quite good. So now the challenge is, okay, let's go to a larger system that's kind of like what you might like to do for molecular imaging, and let's incorporate both the diffractive imaging with the dynamics, right? I mean, right now, this is all dynamics, so they had to work really hard to get all that information with the kinetic energies and run that. So, now with Christoph at Argonne, it makes a good sense to use clusters as a test bed for this imaging. Clusters are kind of, I guess they've been investigated for a very long time. Anyway, but they have their own unique attraction, between atoms and bulk, and then the energy dissipation that you're going to have is not quite like a solid. At least it goes into a vacuum. Okay, so a number of things happen, and this is similar to the C60, but it's like bigger, right? You first start with the ionization, the FDL pulse comes in, you knock off electrons, and you start off with this sort of cluster potential. When you start knocking off electrons, this potential gets lower and lower, depending on the photon energy of your system. You might just be putting some of the electrons sort of inside the system, and some are continuing to ionize. And then when you go out, when all the electrons leave, everything is expanding. I already showed you that for C60, but it also happens in large clusters. And this picture comes from a review article by Argonne here in New Journal of Physics. And the question is, what's the nature of this nanoplasma formation? And you can see it's a complicated problem. And can one recover this initial solid to this nanoplasma transition, which is important for the imaging? And can you recover some of the internal structure? Turns out that Christoph wrote this review chapter in Springer talking about interactions of clusters, rare gas clusters, with the higher energy photons available at synchrotrons and electrons. So one of the things that was done already, there's some data out there. So when we do our calculations, there's something to validate this. There are these Argonne clusters studied at LCLS at 480 eV. And the only thing that was measured in that particular situation was ions. This was actually theoretically motivated by some work by Michael Gross, where he said, in the X-ray regime, everything's backwards, right? You're ionizing from the inside out, etc. And so he actually predicted, the cluster absorption is going to be less than the atomic absorption in the X-ray range, which is completely opposite to what's happening in the optical regime. And so he did this calculation of what the average charge per atom would be as a function of the field strength of the incoming laser. And there were these comprehensive experimental investigations early on at the LCLS, actually also with Christoph and Sebastian Short, and they measure this average charge state versus pulse energy for a family of different pulse durations. This happened to be for a 7-shell argon cluster that has about 1,500 atoms in it. And what you can see, which is kind of interesting, then you can see that the X-ray transparency, which is defined as the amount of extra energy that's required to achieve a particular charge state when you go between these different pulse durations, that it actually, it has some value for an atom, but it goes up for a cluster to some weird peak, and it comes back down again. Which I think, well, this is not totally understood. Maybe it's just a function of the 2 pulse durations that we picked. But in any event, certainly the initial prediction that the absorption in a cluster is less than that of an atom is certainly true. Okay, and so this is one piece of information that we can use to validate. And then the other thing that's come up also is that you can simultaneously measure these long-time dynamics through ion and electron spectroscopy, and also the image that you might actually want to use. And this was initially demonstrated by Thijs Borgo, but also with Christoph, in this PRL back in 2012. And the point is, the ion yields are sensitive to these post-X-ray pulse interactions, and the X-ray imaging is, it's just during the pulse. But if you have both these pieces of data together, you actually have a lot of opportunities for quantitative modeling. Because it turns out that you can, in fact, isolate single pulse, single cluster interactions, because you can tell that for a single cluster, when you hit it, you can determine from its scattering, you can determine its size, because it's largely spherical, and so it has this kind of interesting re-scattering tip. So you can tell the size from the distance between the 2 minima. You can tell the fluence onto that cluster by the integrated area under all these peaks that you have. So you can actually get a pretty good measure of what's going on with that particular cluster. And then the second new tool that one has are these new things that you can do at LCLS. Everything I told you before was just the fact that you have a single SASE pulse coming down, but actually there are these new things that have been developed in the last few years. This one in particular, 2 electron bunches creating 2 X-ray pulses with 2 different colors just came out, and that's being used to do an X-ray pump, X-ray probe experiment, which is quite cool. This is quite cool because you can actually use 2 independent X-ray, 2 independent electron bunches, which can both have lots of gain going through the undulator, so you can get a lot of pulse energy in both of those, as opposed to this configuration where you just have 1 electron bunch, which you do some manipulations with, and use these undulators to get different colors. Okay, so this experiment was very cool. And so what they did was they had these 2 colors that you can produce in these 2 ways. One of them was at 8.39 keV. One was at 8.31 keV. They had, a millijoule of energy in them, focused down to a rather tight diameter. This was in the hard X-ray hall down here. And it was a pretty short pulse. And they impacted it onto the xenon cluster, which was about a 70 nanometer cluster. And it had, about 3 million atoms in it. And they could watch what happened. So the point is that, here you have this pump pulse, this green pump pulse at slightly higher energy. And it goes through the sample. And you only detect the scattering from the probe pulse because you can put this nice filter here that will absorb this blue pulse, because this is right just above the edge of the nickel. And so there's a nickel filter there that just absorbs that pump pulse, and you just see what happens with the probe pulse. And then you can, do a delay between the pump and the probe. And this actually is in press coming out in Science Advances, and that's something that goes along with Science Magazine. And so when you do the single particle analysis on this, it's quite interesting. So you can filter the Bragg reflections for this particular reflection from the FCC lattice. And what you can see as a function of time, so this is increasing probe delay from the cone, is that this Bragg reflection goes out into Q space. And what the Bragg, when it goes out into Q space, it's contracting into real space. And the actual contraction that was found was on the order of a 3% contraction, which is pretty large, right? And then you can also take a look at the intensities as a function of time. And that's given by this so-called, they call it a Debye-Waller factor here. And that's what's plotted here. And you can see at time zero, it's what it is. And then eventually, at these different time delays between 10 and 80 femtoseconds, you can see that it's getting more disordered. And so there are sort of two distinct time constants as the interpretation, right? There's this initial fast electronic damage, and then there's something else that is structural damage or something happening to the cluster. And this is, the point is that the theoretical models, they don't include any sort of contraction. They have, the published ones to date only include expansion, right? And so that was a surprise. Now I learned today at breakfast from that, oh, well, now there's this new theory, theory and experiment, they follow each other, that there's some kind of pick code or something that allows you to do this. But theoretical to date that are out there, they only show this expansion. And there are various explanations as to what it could be that go sort of beyond just, oh, let's simulate and see what happens. But one idea is that there is a metallization occurring here on this very fast time scale. And so similar to, when you have, these are xenon clusters, so they're only bound by van der Waals initially, right? And so similar to when you have like an argon dimer or a helium dimer, and you ionize something, right? Then the next, its excited state is like shifted to, it's like an excimer or something. It's a shorter bond distance. So it's something like that in this longer, in this extended system. And there's another explanation about momentum transfer from the outer charged shell compressing the core. And who knows what's going to happen? Well, it's out for theory, and I gather there's some more experiments going on with this too. Okay, so now how are we going to go about this? Well, we just wanted to, we want to model everything and do a basic calculation of this X-ray diffraction image with the electronic and structural damage. You saw yesterday I showed you what Fei Ho was doing just about charge state distributions, but now and electronic configuration. But now what we want to do is we want to use that to actually calculate diffraction patterns. And so it's basic. It's basically the Thomson cross section times the X-ray fluids and the form factor for the square of the nanoparticle. And of course, the nanoparticle is made up of all these different atoms that have all these different electron configurations. And so all these things get put together and made into a diffraction image. Okay, so how you can do this is actually the other parts of Moore's law that exists at Argonne. we have a very fast supercomputer at Argonne called the Mira. It was actually the fifth fastest in the world at the last benchmark. So there's lots of computing power. There are like 1 million cores in it. And so the idea is that you can do a complete simulation of many of these experimental observables without any detail. And the observables that one has are the ion, the photoelectron, the Auger fluorescence spectra, and now also combined with the X-ray diffraction image. And so the calculations are being done by Fei Ho and Chris Knight, who's actually was a quantum chemist. I should ask him that question. And he's also an expert on large-scale computation of the year. And so the two of them together have been working on this. But it goes beyond those early simulations by Noitz and Zurich because it includes, the resonant excitation I told you about, three binary recombination, elastic scattering from these transient electronic states that weren't included before. And it goes beyond some of these electronic damage studies that other folks have done because many of the electronic damage studies say, oh, well, let's just not worry about any of the nuclear movement. But this one actually also allows that as well. And just as in what's in Robin's case, again, it's quantum processes for the photoionization and these other things. And then once you get into this electron ion plasma thing, then it becomes a classical simulation. But the point is, the other thing, so we looked there, was looking at C60, that was 60 atoms, and then it's associated electrons. But here, it's capable of tracking like 50 million particles. And so it's something that's, the next step that can be done. And so here is an example of what was done for a 7-shell argon cluster, that same argon cluster that I was telling you about that they were doing before, and some diffraction patterns of a number of different fluences. And you can see when you get very high fluences, it's kind of messy already. So what can you reconstruct from that? And we were of course interested not only in what happens to the diffraction pattern, because that doesn't tell you much. What you really want to know is how you can get the reconstruction. So in doing an idealized study on this 7-shell argon cluster, which is about a 5-nanometer cluster, which has all these components to it, and something that's somewhat unrealistic, pulse and lots of photons on it. This is just to get your feet wet and make sure that things actually work. And what you can see is that when you had, this fluence of 10 to the 12 photons per square micron, and even up to 10 to the 14 photons per square micron, you could still see this atomic level information, which is pretty, including all those things, that's pretty good. And so the next step that one wants to go toward here is that, we really need, it's one thing to calculate, there's another thing and to reconstruct, but you have to make sure, you really want to make sure that the simulations that we're doing are actually valid. And so, we want to model the intensity-induced transparency versus cluster size that I showed you, that piece of information. There are also some nice electron energy distributions on argon and xenon clusters up to 1,000 atoms, done by the Japanese group. And there may be some other potential effects that one has to consider to include into the model to make sure that those are working. But sort of on a parallel track to this, and maybe, Margaret, maybe you'll say a lot more about this coherent diffractive imaging momentarily, but we want to be able to do this realistic 3D reconstruction, including the radiation damage. And we did that ideal case where we hadn't added, noise, and we had, all the information was actually available in QSpace, and so then you can actually reconstruct. But, you have to really add those things. And we're testing this orientation algorithm. Basically you have all these random 2D cuts when you actually take your experiment. And you have to figure out what orientation your object was in, and then you have to classify all those things and reconstruct from that. That's a big problem. That was the thing I showed you in the beginning that took so many years for that mini-virus, right? And so we're doing this in collaboration with these folks from Hungary who actually have, who I serendipitously ran into. I said, oh, are you interested? They've actually done some of these initial calculations for radiation damage on carbon clusters with Julia Feigl, and they also have a simplified version of this orientation algorithm. So this should be quite a bit of fun for the future. And so now I get to summarize and quit, and we all get to go to lunch. So just to summarize, I would say many challenges remain toward this 3D dynamic imaging with atomic resolution. That really nice experiment I showed you from Kansas, the ITAMP experiment to understand ultrafast charge transfer nuclear dynamics in this intense regime, it's a tricky problem. And it'd be nice to have some theory, I would for that. This MV simulation seems to work for these bigger things, right? And as I told you, there was this recent paper from the Japanese group that showed it also works for this Argonne nanoplasma. But we think that we have, a reasonable path forward because we have these new tools that are available that we can try to incorporate with all these other computational techniques. The spectroscopy and imaging simultaneous on clusters to define the fluence on the cluster. The X-ray pump, X-ray probe technique, which has this funny observation right away. And then you can combine that with large-scale atomistic computations for these complex systems. And maybe we'll make some progress on this, but this is how science is, right? You kind of go one step at a time. And I should also mention that there is a single particle imaging roadmap in structural dynamics in early 2015. So if you're really interested in this particular thing, you can go look at that. So with that, I'll close and.
So, questions? Yeah.
Linda, I just don't know what the answer is, but do you know what is the highest spatial resolution that, even with the static image, that you can get at the LCD? I just don't know what it is, because if you dynamic with atomic resolution is
that's really challenging. Yes, that's really challenging. Well, if you go to the crystallography guys, they can get out to about 2 angstroms. If you go to crystals, they're very. I mean,
yeah,
that's
but,
what.
Yeah, but not crystals, so because you want them
not
crystal.
right.
Yeah,
I'm not no. So there, it's like 30 nanometers. I think you can even. I mean, it's difficult, right? I think you can do much better in your lab for that sort of thing, and certainly for you can certainly do that at a synchrotron, right?
Yes.
There's no doubt you can do static imaging in a synchrotron, but this dynamic imaging, I would say it's the it's the thing that you can uniquely do.
Yeah.
Right?
Yeah.
So.
Yeah, totally.
When these X-rays were ionizing xenon clusters, I think it was xenon clusters, there were 3 competing, at least theoretical interpretations. Jan-Michael Rost and Will Solomon were one. I think Chris Green had another.
Well, you're talking about at the very low energy, so you're not talking about these high X-ray energies, right?
I'm wondering if there's agreement now on how the energy is transferred, or whether there's still any theoretical disagreement.
I'm not sure that there's so much theoretical disagreement with that now. The idea was that there's some kind of inverse Bremsstrahlung that really helps the absorption process that happens inside, the clusters that doesn't happen, obviously, in an atom. And so that's why you can get the really increased absorption in the clusters versus the atom. But I mean, you can go back and take a look at all these things.
But I mean this idea that you ionize inner electrons and then you get this expansion of the potential. That's a very clean way of thinking about it.
Yeah. Well, these are for much higher photon energies, right? Those were like at those early ones were usually like 15 millimeters or something like that. But some things are cleaner with X-rays, and some things are messier with X-rays, right?
Anything else? Yeah.
So for the 3D image of the virus, how better it is than an electron microscope picture? There was this experiment where they.
Yeah. Well, I think it's not better than an electron microscope picture of something. That particular virus is, there's a size limit that you can do for electron microscopy, and it has to do with sort of the penetration of the electrons. And so, I think things that are bigger than like 150 nanometers or so are very difficult for electron microscopy. They typically, section them and whatnot. So for a whole thing, I don't think you can do it by electron microscopy. It's too thick, right? So it's like a micron-sized object. But I think you can cut it, and then you get, then you can get very high resolution with electron microscopy. Usually you win by electron microscopy.
Well, should we go and have lunch? First, thank you so much, Lina. You have something?
About coming here before 2.
Huh? Oh yeah, don't forget, if